So good morning, everyone. I'm very happy and honored to be in this workshop, and I look forward to a week of interesting discussion and interesting talks. Today I'm going to talk about evolution of dispersal. I would like to acknowledge my collaborators, Stephen Cantrell, Yuan, Benoît, Perthame. So the question is motivated by evolution of dispersal. So there's a conceptual framework in adaptive dynamics where one studies the evolution of dispersal by considering pairwise interaction. So imagine there are different phenotypes of the same species, and you study whether you look at each pair of them, and then ask the question of whether a novel type can invade a resident type. Okay, and if you ask this question for all pair of phenotypes, then one can look at what kind of evolution dynamics they can emerge. Okay, concepts such as evolutionarily stable strategy. Okay, and one can also ask about if you start from a non-optimal phenotype, does this invasion dynamics will it carry the dominant traits towards the ESS, and if it does, how will the trajectory look like? Can we describe the trajectory? So in this respect, it is the it corresponds to the concept of a canonical equation. Okay, and there's also there are many different features, and there's also a feature about evolutionary branching. That is to say, if you start from one phenotype, okay, and then there are situations in the framework where a single phenotype is no longer evolutionarily stable, in the sense that from one dominant traits, then it emerged two cohabiting dominant traits, okay, coexisting, and then which then evolve according to the evolutionary time scale. So this is a conceptual framework, and these kind of things are introduced formally. For instance, a mutation are introduced formally. So one asks if you have a resident, and there comes artificially a certain type of mutation, what happens? So a Hamilton-Jacobi framework was proposed by Dickman et al. In 2005 to rigorously study concepts in adaptive dynamics. So the following model is introduced by Perthame and Bowles, and then study again by Loss et al. So in this model, selection-mutation model, the population is structured by the traits. So we consider a variable u, which describes the frequency of trait z. So each individual has a type, has a label. So z is the label. Okay, and then the frequency evolve according to this mutation selection model. Rho of epsilon is the total population burden. Okay, it's a scalar quantity in this model. And the growth rate is a trait dependent. So the trait here we're interested in is the proliferative advantage. So the growth rate is trait dependent, and it's also a decreasing function in the population burden. Okay, and it is shown in these works that a dominant trait evolves, and it evolves towards fitness maximum. So actually they can describe the movements in the form of a Dirac measure. The support of the Dirac measure, they can describe it using ODE, which is a rigorous form of a canonical equation that was alluded to in the adaptive dynamics. So just a brief introduction of their idea. So what they look at. So Dirac mass is a very singular object. So what they do is they look at the rate function, okay, and then suppose the rate function W epsilon converge, and also suppose after appropriate estimate, suppose also the total population burden converge. They show that the pair of W and rho satisfy the Hamilton-Jacobi equation. Okay, so this is a Hamilton-Jacobi equation in the viscosity sense with an additional constraint, which is a consequence of a population control. So there's a L1 control of the total population, and it manifests itself as this constraint. Okay. So in a sense, if you can solve this Hamilton-Jacobi equation, and then if you can look at where this minimum is attained, then the minimum point of this rate function corresponds to the dominant trait at time capital T. So it is interesting to ask whether this Hamilton-Jacobi equation has a unique solution. So by unique solution, we mean is the pair W and rho is uniquely determined by the Hamilton-Jacobi equation. And so in 2008, Perthame et al. Showed uniqueness for this class of growth rate, capital R. And then in 2016, Merhimi and Hochschoff showed the uniqueness under a convexity assumption in the initial data and the growth rates. And recently, Vincent and myself showed uniqueness under weaker conditions, so coercivity. So if we go back to the problem, we're interested in the dominant traits, capital Z bar. Okay, so the analysis of the original model reveals that rho is an object that lives in BV. So indeed, under the first and third results, the Z bar can have jump discontinuity. In general, it is increasing. Okay, total population burden increasing, growth rate decrease as a whole. But it is a special case when you have convexity, then you can imagine that the rate function W in the limits maintains convexity for all time, and when it moves, the dominant trait also moves continuously in time. So this will actually be useful in the latter part of the talk, so the convexity regime. So there are related works. If you allow time periodicity, then there's a work of Merhimi et al. And then there's also a recent work by Lorenzi and Pouchot, which asks about the equilibrium solution. When does it support multiple Dirac? So now the question I want to ask is, can we study movement traits? Can we study effluence dispersal in it? So the previous model is a proliferative trait. So by movement, I consider a very simple single species model to introduce movement. So X is a spatial variable. The population moves about in a bounded domain, okay? And the phenotypic trait I want to study is the movement rate, so alpha being the dispersal rate. So this is a very nice behaving model. It's a logistic diffusive model. So if you fix diffusion rate alpha, fix a type, then the problem has a single globally attracting equilibrium. Okay, the question originally posed by Hastings in 1983 is to ask what value of alpha. So how does the organism choose alpha? Okay, what type of alpha confers the greatest benefit to the population? Okay. Okay, so using the adaptive dynamics framework, one can ask if you have two types, fast and slow. okay, which type can invade which type and not vice versa. So it is proved by Hastings that the mutants can invade when rare, if and only if it is a slower diffuser. Okay, so in terms of adaptive dynamics, slower diffusion is selected. Later on, Dockery et al. Show that the equilibrium where the slowest species is present is globally asymptotically stable. Okay, so here I want to point out that the invasibility analysis is equivalent to studying an elliptic eigenvalue problem. Okay, where the environment is the dominant species with rate beta, and we ask whether a new species, a novel species with rate alpha can invade. Okay, and a mathematical reason, a principle that behind this two species result is the reduction principle. Okay, which can be described as if you have a static environment, if you have an environment where given by c of x, the growth rate c of x. If it is independent of time, then in general, in higher mixing, decreases growth rate. Okay, higher mixing stabilizes the system. So mathematically, if you consider this elliptic eigenvalue problem, okay, with time, everything is independent of time, then increase alpha increases the principal eigenvalue mu, if you write the eigenvalue in this way. So Dockery et al. Continue to conjecture that, well, if you have more than two species, okay, which are identical except for diffusion, okay, then still the slower diffuser should competitively exclude everything. Okay, so whichever the slowest diffuser that is present initially, it should dominate in the long term. Okay, so this conjecture is as far as I know, still open, and the difficulty is n bigger than 3 is not a monotone dynamical system. So there are less tools for studying global stability results. Okay, so a continuum version of this model is proposed by Perthame and Souganidis in the form of a selection-mutation model with spatial structure. Okay, so here the unknown u is a function of space x, okay, a phenotype trait variable z, and a time variable t. Okay, so if you look at the equation, then the population change is brought about by spatial diffusion. Okay, the space for the diffusion rate is trait dependent. Okay, so depending on what type of the species is, this is a trait dependent spatial diffusion. There's a demographic term. Okay, m of x is a common growth rate for every individual. It is not trait dependent. Okay, and then modified by the total population burden. Okay, and mutation is modeled in the form of a Laplacian in the trait variable, which we'll assume to be small. Okay, so no flux boundary for the space, and then we assume the alpha is a one periodic function in Z. So we assume the solution is also one periodic in Z. Okay, and here the total population burden. So now it is a structured population model with X and Z. Okay, so the total population burden is, we assume competition is local in space. So we integrate at each spatial location the trait variable. So rho is the total population at a certain location X. Okay, and now it is no longer a spatial variable. It is a function of X and T. Okay, so in contrast to the selection mutation model without space, there are less results when spatial structure is included. So this is a partial list, a spatial structure with trait-dependent proliferation. There are work by Mirahimi and collaborators. Our results, our method we're going to present here has more connection with the latter two paper. There's a paper of Joban and Schramm about cancer therapy, drug resistance evolution, where space is explicitly included. And there's also a recent work by Nordman and Perthame where the population is structured by age and traits. So our difficulty is more similar to the latter two paper in the sense that the dominant traits trajectory is one have to look at the equation a short time and then try to figure where this dominant trait is going. So for the selection mutation model, the equilibrium solution dynamics is proved in these two papers, and it is as expected. Okay, so the evolution favors slower dispersal from the adaptive dynamics framework, and indeed in this model, the slowest diffuser is selected at the equilibrium point level. Okay, so if you consider positive equilibrium of this model, and you let the mutation rate go to 0, then the equilibrium solution converges to a Dirac mass in the trait variable. Okay, while it remains regular in the space variable. Okay, so the approach by Perthame and Souganidis is by the Hamilton-Jacobi formulation. So look at the rate function. This time the rate function, okay, u is we write it in exponential of the rate function, and then recall that the rho is the total population. Okay, so so assume that both quantity converges, okay, but it is important to notice that these two quantities used to be related, okay. If you have positive epsilon, then these two quantities relates, well, if you integrate this, this equation with respect to z, you recover rho, okay, but they decouples in the limit. So in the limit, there are really two independent quantities you have to determine. So how to determine the two unknown functions? One can show. So here it is a question of what is the fitness in this evolution model. Okay, in the previous model, the fitness is capital R. Okay, if you are phenotype Z, your fitness is the growth rate. Okay, but in this model, one have to find a kind of effective fitness. If you are type Z, invading a type C bar, what is your how to determine the fitness relative to two traits? Now, at the level of equilibrium solution, it is expressed as an elliptic principal eigenvalue. Okay, so the resident species, the resident population has a spatial distribution rho. Okay, now if you are a type Z, then your effective fitness is some kind of average of in space. Okay, and what kind of average in space depends on the diffusion. Okay, so here the effective fitness is given by the principal eigenvalue of an elliptic eigenvalue problem again. Okay, so where the environment is m minus rho, whatever the population distribution is. Okay, and however, if you look at this Hamilton-Jacobi equation, it is satisfied by W and rho. Both are unknowns. Okay, and how to determine? Does it determine W and does it determine rho? Okay, so here the reduction principle plays an important role again, as in the Dockery results. So we don't have much information on rho. Okay, rho right now we know it's a function, it exists. But the reduction principle is a very general result, which says that whatever rho is, okay, we expect this right-hand side, the effective fitness, to be an increasing function in diffusion. Okay, which means this alpha, which means if this alpha attains a minimum point at C hats, then whenever you are a different type, you have a higher diffusion. Okay, so higher diffusion, and then it translates to this inequality. Okay, which means the right hand side only attains minimum at the phenotype with the slowest diffusion. Okay, so this actually determines everything. So we know the right hand side only has a unique minimum at Z hats wherever the slowest phenotype is. You can go back to the Hamilton-Jacobi equation and show that W has a unique minimum. Okay, if W has a unique minimum, then if you look at this is the interpretation of the rate function, which means U goes to 0 except at C hats. Okay, so one can go ahead and determine everything from this observation. So reduction principle applied to the Hamilton-Jacobi equation determines W and rho at this stage. So this is a reduction principle. So having determined, so there's only one dominant species, which is the Z hats. We can rho is now determined because there's only one species, and we already know there's a single equilibrium, a unique equilibrium when you have only one dominant species. Okay, so the effective growth rate depends on rho, but we know rho. So now we obtain this equation, which again is connected with the adaptive dynamics. So in fact, what is the effective growth rate here? The effective growth rate is the same one where one consider the two species competition. Okay, this is the invasion exponent that tells us whether a type Z can invade a type C hats. Okay, at equilibrium. Okay, and the Hamilton-Jacobi equation tells us another thing. So this is a square, so this is a non-negative term, which means this lambda is positive for all Z. It's non-negative for all Z. Okay, which means that any type Z cannot invade type C hats. Okay, and this is actually the interpretation of the evolutionary stable strategy. Okay, it is a strategy that cannot be invaded by any other type. Okay. So at the equilibrium level, one can say that this is accomplished in a pretty satisfactory way. So this correspondence from the structure population model and the concept in Hamilton-Jacobi equation. So what is open is this question alluded to in the paper of Perthame and Souganidis. Okay, so what they ask is, if this is the Hamilton-Jacobi equation for the equilibrium problem, okay, then can we conjecture that for the time-dependent problem? Okay, so if we look at time-dependent solution in an appropriate time scale, then can we see a moving Dirac? Okay. Okay. At the equilibrium level, we see a stationary Dirac solution in the limit. Can we find a moving Dirac solution if we look at the time-dependent problem and let epsilon to 0? And if so, right, can this dominant trait be described by some kind of Hamilton-Jacobi equation? So motivated by this model, one can ask whether this time-dependent Hamilton-Jacobi equation, if you solve it, okay, and then you look at where the minimum of rate function is, can we similarly obtain some description of this dominant trait? Okay, so first the remark is the conjecture is consistent. Okay, for instance, if you assume there is always a dominant trait, okay, and that it moves it does not jump. Okay, assume this dominant trait moves continuously in time, then indeed the conjecture is consistent. Okay, if you but the problem is that if you look at this problem, the difference between this is a problem with spatial structure and comparing to the problem without spatial structure, one particular difficulty is we do not know how to pass to the limit for rho. Okay, we do not have sufficiently strong estimate for rho. So if you look at the rho equation, this is what we can prove. Okay, and this is due to if you look at the rho equation, it moves in a fast time scale. So there's an epsilon here. Okay, so while we can expect a good regularity in X, for time regularity, this is what one expects. Okay, so whereas in the case without space, we have BV estimate to pass your limit in a more generalized sense. And the second difficulty is, well, if you take the rate function, you get this equation. Okay. Now we expect the rate function to be asymptotically independent of X. The question is, well, we want to derive an equation that is involving the Z variable only. Okay. So, but how to derive this equation? Okay. So we try to apply the perturb test function method. Okay, but that is to say, instead of considering W, we consider a modification of W. Okay, and the question is the choice of a corrector here. Okay, so just as a thought experiment. Okay, so to be close to the spirits of the conjecture, right? We expect the effective fitness to be given by elliptic problem, right? So if we can take the elliptic eigenvalue, okay. If we take the elliptic eigenvalue to be our corrector, take the log, then one can obtain after some calculation, one can obtain such an equation. Asymptotically, it will be independent of X, so we don't mind this term. This is a vanishing viscosity term. So far, so good, okay? Except that we have this remainder term involving the corrector, okay? So the good thing is that it is the elliptic eigenvalue problem, so we know that phi is continuously smoothly dependent on diffusion. So we don't worry about the derivative of the corrector in Z. But this term turns out to be problematic, okay? Because this is a time derivative of phi, right? And this is an elliptic problem. So we only expect phi to be as regular as rho in terms of dependence on time. So this is not necessarily a small term. Okay, so we cannot use this corrector. The second idea for the corrector is to look at a time-dependent problem. Okay, we define phi, we define phi by this time-dependent problem. Okay, we add this term. So if you take this some initial value, take initial value to be 1, okay, and then solve it. So in this case, this term no longer is there. This is absorbed when you apply the equation. But now this term is not regular enough. Okay, and the reason is that this is you're solving this parabolic equation for a long time with the epsilon there. Okay, so for a long time, there's subtle dependence on initial condition, and one may not be regular in the diffusion rate anymore. Okay, so it turns out that the corrector that we need is given by a concept that is called a principal Floquet bundle. Okay, so the thing is we look at the parabolic equation and we look for the solution of this parabolic equation for all time, so for negative time to positive time. Okay, and this object has a strong uniqueness, which enables one to obtain smoothness in the diffusion. Okay, so indeed, with this object, this term is not there, and then we just need to show that this is bounded. This is order epsilon. Okay, and with this character, one can derive not directly to the Hamilton-Jacobi equation we want. Okay, but to approximate one. Okay, so what is the normalized the principal Floquet bundle is the positive solution to this problem. Okay, and there's a unique positive solution as proved in Mersinski and using the abstract results of Polachek and Terezek. It is a generalized notion of principal eigenvalue for elliptic and periodic problems. So here phi and h is the unknown, in the sense that h is the term h is really a normalization of phi. Okay, so the presence of this term h allows one to it arises by the constraint that we require the phi to be constant in L1, for instance. Okay. Okay, so what we need is really the smooth dependence of this object with respect to diffusion rate and other coefficients. Okay, and this is recently established in the paper Cantrell and myself, and with that we can now write down. So what is the upshot? So the original difficulty is we cannot take the limit of rho epsilon to rho. Okay, this was what is done before. Right? We take the limit to rho, we determine rho. Now the difficulty is we don't know how to take the limit rho to. So here what we do is we don't take the limit to rho. For each rho epsilon we can use the notion of principal bundle to define an approximate Hamiltonian, an approximate growth rate. Okay. Okay, so and the next idea is well, we still need to find a candidate for this dominant trait. Okay, and the next idea is we're going to use the approximate Hamiltonian to get a notion of this trait. Okay, so to do that, we just consider this Hamilton-Jacobi equation. Okay, so we can, given having defined the approximate Hamiltonian, we can just write down this Hamilton-Jacobi equation. Okay, so this is now without space. Okay, and this has actually similarity with the original mutation selection model we discussed at the beginning. So the unknown here is V and Z bar. Okay. Okay, and Z bar is a scalar quantity now, right? Just like the rho in the first model. We solve for V, capital V, and we solve for Z bar as the unknown of this equation. Okay, okay, so this question, thanks to Merhimi, Rokshoff, and Calves and Lamb, we can obtain a unique solution of this problem. So one can determine, one can define everything in terms of rho epsilon. From rho epsilon, we have capital H epsilon, and then we have Z bar. Okay, okay. And then one can directly relate W and V by direct comparison because the equations are very similar. Okay, so from here, we know that V has a unique minimum at Z bar, and so do W. Okay, okay. So now W has a unique minimum, and then so we know at a single time, there is a dominant trait, z bar epsilon, and one can use it to determine rho. And this actually improved the regularity in rho because now this z bar is a slowly continuous quantity. It does not behave wildly in time. And this allows to take to the limits. Okay, so it's kind of a so the above what I said before can all be carried out rigorously, assuming one thing, assuming that the approximate Hamiltonian is convex in Z. So well, in general, so it goes. But in general, this capital H, which is a part of the Floquet bundle, it's a hard to control. Okay, so it exists, right? That we have existing uniqueness results, we have smoothness dependence, but it is hard to control. Okay, but we so to control that, we use the fact that well, if rho is stationary, okay, if rho is stationary, then everything, this capital H reduces to the elliptic eigenvalue problem. Okay, so if we can say something about rho being close to stationary, then we can, the convexity, if it is convex in the elliptic problem, it will translate to convexity in this capital H. Okay, so with this kind of idea, one can first do everything I said in a short time. Okay, so everything I said is true for a short time. Okay, everything is well defined. The dominant trait is well defined, and then so for a short time, the original conjecture holds. Okay, so everything is described by this constraint Hamilton-Jacobi equation for a short time, and then we can start again. Okay, and so this is the resulting theorem. Assuming that the elliptic value, which is the invasion fitness, is convex in Z. Okay, so this is related to the choice of alpha. Okay, if alpha is chosen, so that's in this problem, Z is lambda is convex, or lambda tilde is convex, then the dominant trait can indeed be uniquely determined by the Hamilton-Jacobi equation. The consideration of principal Floquet bundle originated from this collaboration, and it turns out to be, well, if you think of the selection-mutation model as a model of infinitely many species, okay, so we have found a concept that is useful for considering competition of species when it is more than 2 species. Okay, and indeed, with the notion of normalized principal Floquet bundle, I revisited the Dockery problem. Okay, so if you have a discrete number of traits, if you have n species, the conjecture is that the slowest diffuser always dominates. Okay, so if we reformulate Dockery's conjecture as follows, okay, consider the collection of diffusion rates, okay, given any capital N, given any increasing sequence of diffusion rates, thus Dockery conjecture holds, okay. So we call the collection of the finite sequence where Dockery's conjecture holds to be a script D, okay. And Dockery conjecture holds if it is the space of all, it is equal to the space of all finite sequences, finite sets. Okay, so what we can prove here, so what Dockery has showed is that for sequence of 2 diffusion rates, right? For all sets of two doubleton sets, it is a subset of Dockery conjecture holds script D. Okay, and what one can prove here is that this script D is open in the Hausdorff sense. Okay, if you consider this script D as a subset of finite space of finite set, it is open. And the main ingredient is the principal Floquet bundle and a Morse decomposition idea due to Conley. So just to wrap up, we treated the situation when this is when the form of the rate function remains convex and this dominant trait moves continuously. So we can do something in this regime. But actually, what is more interesting is that if we go out of this convexity regime, then something interesting that is not observed in adaptive dynamics appears in this structured population model. That is to say, the rate function, if it is non-convex, then something like this can possibly happen. For some time, you have a single dominant trait moving in the negative direction. But what can happen is that this rate function can have more than one zero at a certain time. Okay, in which case one will observe a jump in the dominant traits. Okay, so the missing thing here is that in a short time scale, one will need to use results from two species competition to close the story. Okay, and this is possible to do, but what is more difficult is well, at a certain time there can be any number of zero in the rate function. Okay, so with that, so the conjecture is that actually the continuum problem, Perthame and Souganidis, and Dockery's conjecture, the discrete in trait problem, I think they are related. Okay, so what we can say is if Dockery conjecture holds, then the mutation selection model in Perthame and Souganidis can be well described by this Hamilton-Jacobi equation. Okay, but if Dockery problem is not true, then this may not be adequate. Okay, one may stuck in some regime where there is more than one phenotype that is not in performing non-equilibrium dynamics. Okay, so with that, I want to thank you for your attention.
So thank you very much for the very nice talk. We have time for a few questions, if any, in the room.
Do you have any sense of if there will be a counterexample, or if it should be true?
For a Dockery model?
Yeah.
Yeah, I think it's true, right? There are some people have been trying to use numerics to look at the Dockery, the discrete problem, and they haven't found any. But as far as I know, it's a difficult problem. So.
Thanks.
Thank you very much for the talk. So when W is not convex and touches at two points, I thought the convexity of the minimum played a role.
Yes,
there are some works on the.
Yes, indeed. So the picture is it looks like toy picture, but in general it should look either like this or several because of the solution has a semi-convexity in this kind of problem. So the dominant trait remains discrete. So if one can really treat the finite discrete case, then it connects everything.
Thanks.